Okay. Так, Семен, мы, значит, вышли ли мы на орбиту?
Что?
Вышли ли мы на орбиту?
Да, я говорю, вы в эфире.
Okay. Well, let's recall what happened last time. Given a ring R, we constructed a group K1 of R, and using this from a group, we constructed another group which is called the Whitehead group, and we defined the Whitehead group as the quotient of the K1 of the group ring by some subgroup. Which is generated by the matrices plus minus G, or G's in pi. Now, what's the point of using this group? The point is this: if we have a simplicial pair such that the inclusion is a homotype equivalence, we constructed an element of the Whitehead group, which is called the torsion of the pair. Of course, this element, the way we defined it, for all we know, might depend on the simplicial structure, but in fact it doesn't. Now, let me state two theorems, which one of which I stated last time, and the other one I didn't. So I'll state it today. Well, let me make it one theorem to save on the chalk. Well, suppose we have two simplicial pairs such that this second component is the same. Then these two simplicial pairs. Let's also assume that the inclusion, both inclusions are homotypic equivalences. Then these two pairs are simply homotypic equivalent relative to y, if and only if the torsions are the same. Now, the second statement is the second statement is as follows. Suppose we have a homotypic equivalence, and we want to know when it is homotopic to a simple homotypic equivalence. And the answer is the answer is this is the case if and only if the torsion of hold on. Well, here the first space is the cylinder. Well, the cylinder contains both x and y, but do I want to put an x here or a y, or it doesn't matter? Let's think. One should be careful. The cylinder of a homotypic equivalence is homotypic equivalent to both x and y, but we want more. We want a simple homotypic equivalence. Okay, I think it's an x, but
Я что-то не понял, что ты пишешь, что значит пары, ты имеешь в виду пары?
The torsion is always defined for pairs.
Нет, просто цилиндр F, запятая X. Что?
Значит, цилиндр это выражение.
Цилиндр по F строится.
Да, но значит, он содержит значит, и каноническим образом и
Сколько должна после F?
окей. Anyway, these two theorems are not obvious, and I think we need to have one or several talks about torsion and simple homotopy theory. But now we want to use this torsion to state another theorem, which is the S-cobordism theorem. Which we started talking about last time, but didn't finish. Now we need to define S-cobordisms. How to do that? Well, S stands for simple homotopy equivalence. So there should be a simple homotopy somewhere.
Another question. Does it happen that we have a concrete result of the torsion which is not zero? Are we able to compute sometime?
Yes.
Yes.
Which is again a good topic for a talk. There are computable examples, but they're not for free. In particular, there's one interesting application of torsion, which is proving that some lens spaces are not simply homotopy equivalent.
Actually, you can look at the book of Davis and here, there is the last chapter.
And there are several books which cover this, and lecture notes, etc., etc. The thing is, the problem is even for very easy groups such as the trivial group, the Whitehead group and K1 are not exactly straightforward to calculate. For finite abelian groups, those groups are computable, but it requires some work to compute them. As I said, it can't be done in a minute. So let's hope that someone will volunteer to give a talk on this. And in particular, if you're interested, you can volunteer.
I need to check.
Yeah, actually, well, the source that I suggest is pretty, in my opinion, it is as much clear as
Okay, so let's return to the escobordism theorem. And by the way, there's also lecture notes by Hatcher, which more or less do either the same thing or something similar. I don't remember. It's also worth having a look at. Okay, so we need to understand what an escobordism is. The answer is straightforward. We first require W to be an H-cobordism. This means the inclusion of M naught into W is a homotype equivalent. So it makes sense to talk about the torsion of the pair WM naught, and if the torsion is 0, then the map is sorry, the cobordism is an escobordism. Now let's assume that the manifolds have a dimension which is sufficiently high, greater than or equal 5. Same as for H-cobordism. Then the cobordism W is diffeomorphic to M naught cross 0, 1 relative to M relative to M naught, which is identified with itself cross 0. Again, the conclusion is the same as in the case of the H-cobordism theorem. The only difference is this condition on the torsion. What next? Next, we want to prove this theorem, and to do that, we we need to get a handle on the torsion. We need to we need to be able to relate this tau with handles, which were had in the proof of the H-cobordism theorem. And I want to make some simplifying assumptions. Namely, I want to assume M naught orientable because I want to I will shortly want to calculate the intersection indices of various things. If this is not the case, well, this was automatic in the simply connected case, but if
your intersection index will be
yes, in general, the intersection index will be in the cohomology with the coefficients in some local system, and well, let's not worry. Let's just make this assumption and not worry about that. Now we want to construct this tower using the Handel decomposition. To do that, I need to I need to have an isomorphism of Z pi modules. With basis. And first of all, I choose a base point, and well, for each instead of just handles, I consider pairs H gamma, where H is a handle. And gamma is a path from x naught to to the center of the handle. In particular, there are as many couples as for each h for each given h as there are elements in the fundamental group. And we consider paths obviously up to homotopy with fixed endpoints. Now I want to calculate the intersection index of two handles, or more precisely, the incidence coefficient of two handles. Suppose I have two handles and I want to calculate the incidence coefficient. Well, the construction is the same as in the simply connected case, except this time we need to take the fundamental group into account. Well, suppose we have one handle of index q and another handle of index q minus 1. In the h cobordism case, we needed to intersect the attaching sphere of one of them with the belt sphere of the other. Now, let's try to remember which sphere goes where. Now, let's see. the attaching sphere of which handle? Well, let's see. So let's draw a handle. So, is it the attaching sphere of the higher index handle or the lower index handle? Yes, H Q alpha and the bell sphere, and by exclusion H Q minus 1 beta. Okay. Now I need to define. Well, the sign is the sign of the intersection point is defined in the same way as for in the H cobordism case, and the group element is. Well, the group elements is as follows. We first go from the base point to the center of the lower of the handle of the lower index. We arrive somewhere inside the handle. Then we go to the intersection point of the belt sphere of the lower index handle. And this point is inside the higher index handle as well. So we can construct a path from the intersection point to the center of the other handle, HQ alpha. And then we take the path gamma alpha to the minus 1. And then we take the class of this. We get a loop, and we take the class of this loop in the homotopy in the fundamental group. Well, if we believe that the handle complex in the simply connected case calculates the relative homology, it's not too hard to believe that first of all, we have defined the incidence coefficient, but then it's straightforward to define the differential and well, let me denote this this incidence coefficient. In the same way as for in the simply connected case, and then the first remark is we did what? We defined this this incidence coefficient as an element of the group ring. Now, my claim is that using this, we get a differential delta on the chain complex with which is generated by the handles. In other words, we here we use threaded handles. What does this mean? Handles plus couples apart from the base point to the center of the handle. Now, this definition is equivalent with respect to the action of pi 1 of pi 1 of W. Well, how does pi 1 of W act on threaded handles? Just by concatenating those gammas with elements of pi 1. Does this make any sense?
The only question is if you are writing down the path, the loop or its inverse before the path.
Well, let's say we
I think inverse because in order to make it action.
well, there are left actions or right actions.
It is right action.
Well, yes. Well, and also some people write the result of concatenation to loops in this order, and some use the opposite order. Well, it's very confusing and and it's
anyway. First you can make a loop and then you make a path.
well, I suggest we and this will not be very important to us in the sequel. So I suggest we just not go into this type of questions. Even with permutations, it's not obvious. Some people write the product of two permutations in this order, and some in the opposite order. And well, it's one of those questions which yes, exactly. Anyhow, the end result is that we get a chain complex of z pi 1 modules, which has a preferred basis once once we have chosen a preimage of x naught tilde inside W tilde. Now we we construct the element. We construct the torsion of this complex as as we did last time, and this gives us an element of the Whitehead group, and my claim is this is the same as the Whitehead as the torsion which we defined last week or earlier today. Now the next step is to construct the next step is to prove the Whitehead theorem, and the Escobar-Wadism theorem, and we this is where we stopped. This is where we stopped last week. So if I have a chain complex with a based chain complex, meaning a chain complex with a basis, and if this complex is a cyclic, I can construct the Whitehead torsion as we saw last week. Now, supposing the torsion is where for general rings, instead of taking the quotient with respect to the subgroup generated by plus minus g, I simply quotient out the plus minus 1 and well, I get some quotient of k1. Which some people also call k1 tilde. Anyhow, suppose the torsion is 0. Then my claim is yes, my claim is the chain complex which I want to denote C level star and my claim is, in this case, the chain complex can be transformed into a direct sum of of the trivial chain complexes by using operations by using the following operations. Well, the first operation is where we got stock last time, and the operation consists in choosing a different basis.
Just one element changes.
One element gets replaced by itself plus some
Plus one
plus g times another.
You mean that?
Oh, sorry. Yes. Well, let me do it one step at a time. So g. So I take one element and replace it with itself plus g times another handle of the same index.
And g is what?
And g is inside by 1. And basically, the first remark. This is realizable by handle slides. So we change just one element, we leave all other elements as they were.
Yeah, so the only thing you have to specify how you make this change.
How do we make this change in? By the way, while we're at it, let's do plus or minus. Where minus is realizable in the same way as it is in the h-cobordism case. Now, how do we do this in the h-cobordism case? How do we realize this this using handle slides in the h-cobordism case? Well, suppose we have two handles, and then we have the attaching spheres of those handles, and we proceed as follows. We take the attaching sphere of this, and then we by deforming it, we bring it close to the attaching sphere of this handle, and then we take the connected sum of the two spheres, and we get another sphere, which is the attaching sphere of the new handle. Now, the same thing happens in the non-simply connected case, except there are many ways in which one sphere can approach the other sphere. How many? Well, as many as there are elements in pi1. And
by approaching, you just mean you connect a point on one sphere by the path.
Yes.
With a point of the other sphere.
Yes, and then
try to move one here along this corridor.
along a small neighborhood of the path. And then the problem is there are many paths, and
without loss of generality, you can move it through. I mean, how to apply the P1? I mean, you can move it you can take this path passing through the distinguished point.
Well, not necessarily. It just suffices to remember that there are as many paths with fixed endpoints as there are elements in pi1. And by choosing, by letting the path run through all possible classes with homotopy classes with fixed endpoints, we get all possible elements G here. Okay. Well, we're supposed to have a break. Let's have a break until when? Okay. Well, let's. I don't know. Let's have a break. How much time do we need? Well, let's have a 10-minute break.